Somewhere, 400,000 miles past the orbit of the moon, a gold-coated mirror the size of a tennis court is staring into a place that should not exist. Not a black hole, not an alien signal. Something quieter and somehow more disturbing to the people whose entire careers were built on knowing how the universe works. A galaxy. Just a galaxy. Except this one was fully formed, fully massive, packed with stars, sitting in a part of the sky that represents a time when the universe was only 280 million years old. For context, that is roughly 2% of the universe's current age. It is the cosmic equivalent of finding a fully grown adult standing in a delivery room. And it is not the only one. Astronomers now have a name for what they keep finding out there, and it is not a flattering one. They call them impossible galaxies. Because according to the physics that has guided cosmology for nearly a century, these things simply should not be there. Not yet. Not this early. Not this big. And every single month, the James Webb Space Telescope finds another one, quietly, patiently, dismantling assumptions that were considered settled science before it ever left the ground. This is not a story about a telescope taking pretty pictures. This is a story about a machine that was built to confirm what we already believed about the birth of the universe, and instead has spent the last several years handing scientists one uncomfortable surprise after another. Some of the world's most respected astrophysicists are now openly saying that our models of galaxy formation need to be rewritten. Not adjusted, rewritten. And if you think that sounds dramatic, stick around, because by the end of this, you're going to understand exactly why a piece of hardware orbiting near the second Lagrange point has some of the smartest people on the planet quietly worried that we got something fundamental wrong. Let's rewind for a second, because you need to understand what Webb was actually supposed to do. When it launched in December 2021, riding an Ariane 5 rocket built through a partnership between NASA, the European Space Agency, and the Canadian Space Agency. Its main job was to look further back in time than any instrument humanity had ever built. Not metaphorically, literally back in time. Light takes time to travel, so the further away something is, the older the light is when it finally reaches us. Webb's mirror, 6.5 meters across and built from 18 hexagonal gold-coated segments, was designed to catch the faint infrared glow of the very first galaxies, the ones that formed in the chaotic aftermath of the Big Bang. Scientists expected small, faint, messy blobs of young stars, primitive building blocks, the kind of thing you'd expect from a universe still figuring out how to make galaxies at all. That is not what they found. Here's a detail that makes this even more unsettling. This isn't even the first hint of trouble. Years before Webb launched, the Hubble Space Telescope caught an early warning sign, a surprisingly bright galaxy called GNZ11, existing just 400 million years after the Big Bang. At the time, it was the most distant galaxy ever confirmed, and it was already brighter than it had any right to be. Astronomers noted the strangeness, filed it away, and largely assumed it was an outlier, a weird exception. The kind of thing that happens once in a rare while in a universe of hundreds of billions of galaxies. Webb was supposed to settle the question, confirm GNZ11's distance, and move on to the real work of mapping out the calm, orderly, predictable galaxies scientists expected to dominate the early universe. Instead, Webb confirmed GNZ11's extreme distance and then kept finding more galaxies just like it. Brighter, earlier, bigger. What looked like a one-off exception turned out to be the first crack in the wall. As one member of the MOMZ14 research team, graduate student Yijia Li of Penn State, put it, it's an incredibly exciting time because Webb is revealing the early universe like never before and showing scientists just how much there still is left to figure out. That's the polite, careful, academic way of saying, we thought we understood this, and we were wrong. One of the clearest examples is a galaxy called MOMZ14. Using Webb's near-infrared spectrograph, astronomers led by researcher Rohan Naidu at MIT's Kavli Institute confirmed this galaxy sits at a redshift of 1444. In plain terms, its light has been traveling toward us for about 13.5 billion years, out of the universe's total age of roughly 13.8 billion years. That places it just 280 million years after the Big Bang. And it is not some faint smudge. It is bright. Genuinely, surprisingly bright. Bright enough that it forced the research team to admit their own predictions were wrong. In their words, the early universe looks nothing like what was expected. This isn't a one-off anomaly either. According to the team behind the discovery, galaxies like this one are showing up roughly 100 times more often than theoretical models predicted before Webb ever launched. 100 times. That is not a rounding error. That is a sign that something in the underlying theory is broken. Now, here's where it gets stranger. Because it's not just that these early galaxies are bright. It's that they're organized, structured, mature in a way that shouldn't be possible so soon after the universe's birth. Take the galaxy nicknamed the Big Wheel. Webb discovered it sitting in a field that was originally chosen because of a bright quasar nearby. And what it found there stopped astronomers in their tracks. A massive spiral disk galaxy, 5 times more massive than our entire Milky Way, complete with visible spiral arms, existing just 2 billion years after the Big Bang. That means, when the universe was only about 15% of its current age, this thing already had the kind of large, orderly, rotating disk structure that our models say should take much longer to build, and more importantly, to survive. Spiral arms are fragile. They get disrupted by collisions, by gravitational chaos, by the sheer violence of a young, crowded universe. And yet, here was one, fully intact, fully massive, at a point in cosmic history when everything was supposed to still be a disorganized mess. Hubble, looking at the same patch of sky in ultraviolet light, only ever saw scattered clumps on the outskirts. It took Webb's infrared vision to reveal that underneath those clumps was an entire, coherent, rotating disk of older stars that Hubble had been completely blind to. The scientists studying it put it bluntly: this discovery is a demanding test of how galaxies grow, and right now, the models are failing the test. And if a fully grown spiral galaxy showing up too early wasn't enough to make you uneasy, consider this one. In January 2026, a team from Texas A&M University, led by postdoctoral researcher Wade Hu and Professor Casey Popovich, identified something in the data that nobody expected to see so soon after the Big Bang. An active, tightly packed collision. Not one galaxy, not two. At least 5 galaxies, merging together only about 800 million years after the birth of the universe. They nicknamed it JWST's Quintet. And it wasn't just galaxies smashing into each other for the sake of spectacle. The collision was actively redistributing heavy elements, the products of stellar fusion like oxygen, flinging them out beyond the galaxies themselves and into the surrounding space. Before this discovery, astronomers expected this kind of complex merger and this kind of widespread chemical enrichment to become common only after more than 1 billion years had passed. This was happening hundreds of millions of years ahead of schedule. Professor Popovich said it plainly. This tells us that our theories of how galaxies assemble and how quickly they do it need to be updated to match reality, not tweaked, updated. That is a scientist, on the record, admitting the textbook is wrong. It doesn't stop there. A separate international team, led by researchers at Leiden University and the University of Oxford, went looking for something specific. Radio telescopes had picked up strange emissions coming from a distant patch of sky, emissions that hinted at an active supermassive black hole feeding on surrounding material. When they turned Webb toward the source, cataloged as TGS-SJ 1530+49, they expected to find one galaxy housing that black hole. What they found instead was an entire construction site. At least 6 galaxies, packed together in a region only a few tens of thousands of light years across, all in the process of merging into a single colossal system. 4 of those 6 galaxies were already surprisingly massive on their own, together holding hundreds of billions of solar masses worth of stars, crammed into a space that, on cosmic scales, is almost claustrophobically small. And this is happening in a universe that was only about 1.5 billion years old at the time. Researcher Ayush Saxena of Oxford said it best. They went looking for a single black hole and instead found an entire complex of galaxies feeding it. At the center of all that chaos, a supermassive black hole is growing in real time, right alongside the galaxy that will eventually contain it. It's a rare, live snapshot of exactly the kind of runaway growth that current models struggle to explain happening this early, this fast. And speaking of black holes, there's another discovery that quietly undermines a relationship astronomers thought they understood. In nearby galaxies, there's a well-established pattern. The mass of a galaxy's central black hole tracks closely with the properties of the galaxy around it. It's one of the more reliable rules in modern astrophysics. But researchers at Carnegie Science used Webb to measure, for the first time, the mass of a now-dormant black hole from the early universe, inside a galaxy called MRG M0138. What they found suggests that in the densest environments of the early cosmos, black holes were growing explosively fast, likely powering a quasar phase violent enough to blast away the very gas that fuels star formation, effectively shutting the galaxy down early. Only, in other words, some of these ancient galaxies may have burned out young, their growth cut short by the very black holes sitting at their hearts. It raises an uncomfortable question that nobody has fully answered yet. If black holes were already this dominant, this early, was the relationship between galaxies and their black holes actually built the other way around from what we assumed? Then there's a galaxy that breaks a different rule entirely. Not a rule about size or speed, but a rule about motion itself. In a study published in Nature Astronomy, researcher Ben Forrest and his team at the University of California, Davis studied a massive galaxy that formed less than 2 billion years after the Big Bang. Under normal circumstances, young galaxies are expected to be spinning. Gas flows inward. Gravity pulls. Angular momentum builds and the galaxy starts to rotate, the same way water spirals down a drain. That's the model. That's what should happen. But this galaxy, cataloged as XMM-Vid1 2075, showed no evidence of rotation at all. None. That is a trait typically reserved for much older, much more evolved galaxies, ones that have had billions of years to settle into that kind of quiet, static state. Forrest called it surprising and very interesting, which in scientific language roughly translates to, we don't fully understand what we're looking at. This galaxy had already stopped forming new stars, already packed in several times the stellar mass of our entire Milky Way, and already skipped the spinning phase that every model says it should have gone through. It's as if this galaxy fast-forwarded through its own life story. Even the shape of galaxies in the young universe is turning out to be stranger than expected. Researchers at the University of Waterloo, digging through Webb's observations of the cosmos field, identified the most distant jellyfish galaxy ever recorded, a galaxy trailing long, tentacle-like streams of gas and newborn stars as it plows through a dense cluster, exactly the way real jellyfish trail their tendrils through water. This particular galaxy is seen as it appeared 8.5 billion years ago, and its existence tells astronomers that the early universe may have been a far more violent, far more turbulent place than the calm, orderly picture painted by earlier models. Galaxies weren't drifting peacefully through empty space. They were being ripped apart, stretched, and reshaped by forces far stronger than anyone anticipated. Now, physics being wrong about galaxy formation is one thing. It's a big thing, don't get me wrong, but it's still physics, arguing with physics. What happened next is the part that makes this whole story personal, because it edges toward a question every single one of us has asked while looking up at the night sky. Are we alone? In the atmosphere of a distant world called K2-18b, a planet orbiting within the habitable zone of a red dwarf star roughly 120 light-years away, Webb detected a chemical signature. On Earth, that particular molecule, dimethyl sulfide, is produced almost exclusively by living organisms, mostly marine phytoplankton. Its presence in an alien atmosphere would be, without exaggeration, one of the most significant scientific findings in human history. Here's the responsible part of the story, though, the part a lot of headlines conveniently leave out. The signal currently sits at a 3 sigma confidence level. In scientific terms, that's meaningful, but it is not yet the 5 sigma threshold that astronomers and physicists require before they'll stand behind a formal claim of discovery. NASA itself has been careful and precise about this, stating plainly that they are not claiming to have detected life on K2-18b. What they are saying is that they've found a chemical signal significant enough to demand urgent, serious follow-up investigation. That's not a letdown. That's how real science is supposed to work. No premature victory laps, no manufactured certainty, just a genuinely tantalizing signal that the entire astronomical community is now racing to confirm or rule out. So step back for a second and look at the shape of everything Webb has handed us. Galaxies that are too big, too bright, and too structured for a universe their age. Mergers happening hundreds of millions of years ahead of schedule. Black holes growing so fast they may be shutting down the very galaxies that host them. A massive galaxy that skipped its own spinning phase entirely. Violent, jellyfish-shaped galaxies being torn apart in the early cosmos. And now, a possible biosignature sitting on a planet outside our solar system, right at the edge of what current instruments can even detect. None of these are science fiction. Every one of these is a peer-reviewed finding, published in journals like Nature Astronomy and the Open Journal of Astrophysics, backed by research teams at MIT, Oxford, Leiden, UC Davis, Waterloo, Texas A&M, and Carnegie Science. This is happening right now, in real time, and it is happening faster than the scientific community can update its own textbooks. Here's the thing that should genuinely give you chills. The standard model of cosmology, the one built on decades of careful observation and mathematics, the one that predicted a slow, orderly, gradual buildup of galaxies over billions of years, is being challenged by direct, repeated, undeniable observational evidence. And this isn't a fringe theory being pushed by outsiders. This is coming from inside the mainstream. From the researchers who built their careers on the old model, now standing in front of their own data, admitting that reality does not match the prediction. When a Texas A&M professor tells you the theory needs to be updated to match reality, that is as close as you'll ever get to a scientist saying quietly that we might have gotten the story of the universe's youth wrong. And Webb is nowhere near finished. When it launched, engineers designed it with enough fuel for a 10-year mission. But the Ariane 5 rocket that carried it into space was so precisely targeted that Webb burned far less fuel correcting its trajectory than anyone expected. Current estimates from NASA suggest the telescope now has enough propellant to keep operating for at least 20 years, potentially stretching its mission into the late 2030s or beyond. That means this is not a story with an ending. Every few months, somewhere in the world, A research team is going to point this telescope at another patch of ancient sky, and there's a very real chance they're going to find something else that doesn't fit. Another impossible galaxy, another merger too early, another black hole too massive. Maybe, eventually, a biosignature strong enough to cross that 5 sigma threshold and change everything we think we know about our place in the universe. Let's talk about why this actually matters, beyond the raw thrill of watching scientists get surprised over and over again. The dominant framework in cosmology is often called the lambda CDM model, built on the idea of a universe shaped by dark energy and cold dark matter, expanding and cooling in a fairly predictable rhythm since the Big Bang. That model has been remarkably successful. It correctly predicted the cosmic microwave background, the large-scale structure of the universe, the abundance of light elements. It is not a fringe idea. It is the closest thing modern cosmology has to a foundation. And that's exactly why the impossible galaxies problem matters so much. When galaxies show up looking 100 times more massive and more common than lambda CDM predicts at those early epochs, scientists are left with a narrow set of uncomfortable options. Either stars formed far more efficiently and far faster in the infant universe than any simulation currently allows, which would mean rewriting the physics of star formation itself. Or something about the standard cosmological model. The very framework underpinning modern astrophysics needs fundamental revision. Neither option is small, neither option is comfortable, and right now nobody knows for certain which one it's going to be, or whether the answer is something nobody has even proposed yet. There's a reason this keeps happening with Webb specifically, and it comes down to a very simple piece of physics: dust. Earlier telescopes like Hubble were built primarily to see visible and ultraviolet light, but by the time light from the very first galaxies reaches us, the expansion of the universe has stretched it dramatically, shifting it out of the visible spectrum entirely and into the infrared. Hubble was essentially near blind to huge portions of what those ancient galaxies actually looked like. It could see the young, hot, blue stars flaring on the surface, the ultraviolet glow, but it missed the older, cooler, more massive stellar populations hiding underneath, the ones that actually carry most of a galaxy's mass. Webb's infrared instruments were purpose-built to see exactly that hidden material, and when scientists finally pointed Webb's infrared eyes at galaxies Hubble had already mapped, entire structures appeared that were completely invisible before. That's exactly what happened with the big wheel. Hubble saw scattered clumps. Webb revealed an entire massive rotating disk hiding in plain sight. In a very real sense, we weren't wrong about the universe being strange. We simply couldn't see how strange it actually was, until now. Teams at MIT, Oxford, Leiden, Texas A&M, UC Davis, Waterloo, and Carnegie Science, working independently, using different instruments on the same telescope, pointed at completely different regions of the sky, are all converging on the same uncomfortable conclusion from different directions. One team finds galaxies too bright and too early. Another finds mergers too complex and too soon. Another finds black holes too massive too fast. Another finds a galaxy that skipped its own developmental stage entirely. When results like that keep stacking up from unrelated groups studying unrelated targets, scientists stop treating them as isolated curiosities. They start treating them as a pattern. And right now, the pattern points in one direction. The early universe built itself faster, denser, and more violently than the models currently allow. We built a machine to confirm what we already believed about how we got here. Instead, it keeps looking back at us with pictures that don't make sense, forcing some of the smartest people alive to admit, again and again, that the universe grew up faster, stranger, and more violently than anyone predicted. The question now isn't whether Webb is going to break another assumption. It's when and how big the next one is going to be. Because somewhere out there, in a patch of sky nobody has pointed a telescope at yet, there is very likely another impossible galaxy waiting. And the moment we find it, the story gets rewritten all over again.